This video is continuing from the last video, stoichiometry for multiple choice. So this is a free response. Now, number one, steel is a combination of iron and many other ingredients. So you need to make a 20 milliliter of each of the following: iron, Fe3 plus a standard solution, 0.25 molarity, 0.5 molarity, 0.75 molarity, and 1 molarity. These samples are made from the stock solution of 2 molarity FeCl3. Now, first part, explain using calculation and experimental procedure. So you have to show calculation and experimental procedure. So how you would prepare 150 milliliter of 2 molarity FeCl3 solution with solid iron chloride and necessary lab equipment. So I'm gonna prepare that. So what do you need to have? I need to find out then first of all how many mole of FeCl2. So they gave you milliliter and molarity, so you can find out mole of FeCl3. So let's just start from 2.00 molarity FeCl3, and then so this one times, right, times a 0.150 liter will give you how many mole, right? So then if you multiply it out, then you get 0.300 mole, okay, of FeCl3. Now, so that much more you need to prepare. So now, so how you gonna make that much more? So I need to find out then how many grams of that, like solid, right? So then I can find out one more using molar mass of FeCl3. 1 mole of FeCl3 is when you use a periodic table to find out molar mass of FeCl3, then you're gonna get 162.205 gram. Okay, then if you use a calculator, when you multiply that, approximately 48.7 gram of FeCl3 that's solid. Okay, so that much gram you're gonna need to have it, okay, in order to make 150 milliliter of 2 molarity. Now, but that is a solid, so how you gonna, what kind of equipment you're gonna use? So what you have to do is dissolve this, because this is a solid, right? Solid ion. So dissolve, you can say 48.7 gram of FeCl3 in 150 milliliter volumic flask using volumetric flask. Okay, and then fill the line. Okay, fill up to the line. Okay, fill up to the line, which is 150 milliliter. Using that exact 150 milliliter volumetric flask, and then fill the line. That's what you have to do. Now, second one, explain using at least one sample calculation. So how would you make the full standard solution? Okay, so the way you have to do is, first of all, then I need to find out what is a volume then, right? Using that 2 molarity. So what you have to do is, so here 0.25 molarity first. So then you can say 0.25 molarity, right? Times you're gonna need 20 milliliter each one, so 20 milliliter. So M1V1 is M2V2, right? So so 20 milliliter of 0.25 molarity, but what you have is here 2 molarity, right? So 2 molarity times your V2, right? So if you compute, so V2 is when you use a calculator, you're gonna have 2.5 milliliter. Okay, so 2.5 milliliter. So now what you have to do is you can say it this way then. Take 2.5, take 2.5 milliliter of 2.00 molarity of FeCl3 stock solution. Okay, stock solution, and dilute. Okay, dilute with distilled water. Distilled water to total volume of 20 milliliter, right? To total volume of 20.0 milliliter, because that's what you're gonna need, right? 20 milliliter here. Okay, so that's what you have to do. Now then, it said that how would you take other 4 standards? So you need to find out then how many 2 molarity of like each one, right? How many volume you need. So basically, like if you do next one, instead of 0.5, you do 0.50 times 20 equals 2 molarity and then V2. Then what you have is your V2 is like 5.0 milliliter. Okay, things like that. So I'm not gonna do every single one, but the other 4 is so then I'm gonna just write down the answer. So the other 4 other solution you're gonna need so 5.0 milliliter for 0.5 molarity, right? And next one is a 7.5 milliliter for 0.75 molarity, and 10 milliliter, right? 10 milliliter for your here 1 molarity. Okay, that's the how you're gonna prepare. Now Beer's law plot was created from standard solution, which yielded the following graph. So this one is we call Beer's law. So it's observance on the y side, and then concentration is x side here. So what is basically Beer's law? Beer's law is basically there is a linear relationship. So I'm gonna write down here. So Beer's law is state that there is a linear, okay, relationship between the concentration and the observance, right? Observance of the solution. Okay, that's what Beer's law. So as you see, there's a linear relationship. So this one tells you 15 milliliter aliquot that was prepared the volumic flask from dissolving the screw had a observance 0.1837. Okay, that is observance. Observance is y value. Okay, that is y value. And I find the concentration of iron steel. So find out which is a percentage of the iron for the screw if the screw you dissolved in the flask had mass of 0.3112 gram. Okay, so I'm gonna start here. So then you're gonna start with that y value. So I'm gonna use that equation right here. This equation right here they gave you. So I'm gonna substitute that y value 0.1837 equals 0.344x plus 0.065. So if you compute your x value, which is a concentration, you have 0.345 molarity. Okay, using calculator you can get x value. Now, so we found out that molarity, then find the percentage of iron. So in that molarity, how many grams of that ion you're gonna have, right? So 0.345 molarity. So I need to find out more. So you multiply then liter. Liter is right here, right? So basically then changing to liter, so that times divided by 1,000, so 0.015 liter. That will give you how many mole? So if you multiply 0.00518 mole of, you have Fe3 plus. Okay, that's what this ion. So then I need to have then that one mole of Fe3 plus is how many your molar mass. So if you use a periodic table, that's 55.847 gram. Okay, so when you multiply, I got 0.289 gram of Fe, right? 3 plus. So, but it's a gram, but what is a percentage math? So that divide by, then they gave you, it said dissolve the tank, the mass of this, right? So out of that mass, that much mass is ion. So 0.3112 gram of your mass. That times 100, if you multiply, then that you're gonna get 93.0%. Number 2, refer to the below equation for the following. So MnO4 1 minus, and then NO2 1 minus, and there's MnO2 precipitation, and NO3 1 minus. Now use acidic conditions to balance the above redox equation. Okay, so redox equation is one side is reduced and the other one is oxidized. Okay, reduced means it accepts the electron, and then oxidation means it losing the electron. Okay, so let's look at an MnO4 first. Oops. MnO4 minus 1 minus. Now that becomes MnO2. So then when you this one dissolve in the water, so this, where is this O2 go? So it makes water, H2. Then of course you need to have H plus in the water, right? Hydrogen ion. So then plus MnO4 will be MnO2 and plus water. That's a liter. Now, so how many you're gonna need, right? So here you have O4, right? So then this one you have a 2O, and this one also you're gonna need 2. Now how many H you need? Then 4H, right? So that's basically what that is. Now then if you look at it, so how many electrons you can here, which is a reduced, so reduction, right? So how many electron goes in here? So what you have to do is now here H plus. So if you look at this manganese here, O is a 2 minus, but times a 4, which is a negative 8. But to be negative 1 charge, the manganese should be plus 7. Now here, so O is also 2 minus, but times 2 is a minus 4. So to be no charge, that means this manganese should be plus 4. So that means it accepts 3 electrons. So you're going to have 3 electrons like that. Okay, so that's a reduction equation. Now, what about oxidation side? So then you can say that NO2, right? Now this one, minus 1, that becomes NO3, 1 minus, right? So now, so then this one, water should be added here, right? In order to get more O here. then of course 2H plus to balance out, 2H plus will come out. Now when you look at your electron then here, so O is a minus 2 times 2 is a negative 4, but to be negative 1 charge, then N is nitrogen, you're going to have a plus 3 charge. Now here, similarly, negative 2 times 3 is a negative 6. So to be negative 1 charge, nitrogen is a plus 5 charge. So then you lose a 2 electron, right? So then plus 2 electron like that. Okay, now charge also balance. So this is a oxidation. Okay, so that's why we call redox equation. Now, next step, this number of electron should match. So what I have to do is that this one here, this one times 2 to have a common multiple 26. Now here, this equation you multiply then 3. So both of them you're gonna have a 6, right? So then let me rewrite it here, up above here. So then you have 6 electron plus times 2, so 8H plus and 2 MnO4. Oops, this one should be plus 2 MnO4 minus, that's a 2 MnO2 plus 4 H2O. Okay, and the other one when you multiply by 3, so 3 H2O plus 3 NO2 minus, that will be 3 NO3 minus and plus 6H plus 6 electrons. So now let's add up. So this one cancel. That's why you multiply that 2 and 3 each equation. Now so H1 here, it will be then 2H plus. Okay, kind of cancel out. Now the other one you see Mn, let's see when you add up. Another one water here, right? So you have water, you have only one H2O this side. Okay, so 2H plus, then I'm gonna write down the rest of it. 2 MnO4 minus, and then plus 3 NO2 minus. That becomes, that was a reaction side. Now product side is then 2 MnO2 plus H2O and then plus 3, right? 3 NO3 minus. Okay, so I'm done. So that's your final equation for that. So that's a balanced equation. That's your final answer. Now let's look at C. What is the theoretical yield in grams for solid MnO2? And if a 14.5 milliliter of 0.15 molarity MnO4 minus is reacted with a 12.75 milliliter of 0.17 molarity NO2 minus. So what do you need to start is let's then find out which one is a limiting reactant. So when you look at here, so compared to this one and this one, which one is a limiting reactant? So let's find out more first. Then MnO4 minus is you have this. So then 0.15 molarity times, you divide by 1,000 to change into liter, 0.014. So I have to say 0.01450 liter. Then when you multiply, then you get 0.002175 more of MnO4 minus. Okay. And the other one is 0.17 molarity right here, NO2, times 0.01275 liter. Then when you multiply, then 0.002168 more of NO2 minus. Now, to find out limiting reactants, so you have to divide by coefficient. So that divide by MnO4 is right here, is a 2. Okay, so divide by 2. Then you get, let me see. That divide by 2, 0.002175 divided by 2 will give me 0.001088. Okay, and this one NO2 coefficient is 3, so you divide by 3 here. So 0.002168 divided by 3, so I got 0.00723. So this 0007, so you have 1 mole. So this is way smaller. So this is a limiting reactant. Okay. So now, then since you found out limiting reactant, so you work with that. So then I'm gonna start from then this. Okay, that limiting reactant. So you're gonna say 0.002168 mole of NO2 minus. Now, so you need to find out MnO2, right? What is the theoretical yield? So how many grams of that? So how many moles of MnO2? So if you look at here, the ratio is for NO2 3 to 2, right? The ratio molar ratio 3 to 2, this one. So then 3 more of NO2 minus, and you're gonna have 2 more of MnO2. Okay, so and then also 1 more of MnO2. So dimension analysis, when you look for that molar mass of MnO2, then you will get 86.9388 gram. Okay, so when you multiply it out, you're gonna need then 0.1257 gram of MnO2. Okay, so that's the theoretical yield in grams of MnO2. Okay, when you react with that using limiting reactant. Now let's move on to determine the concentration MnO4 minus after reaction is complete. Okay, after the reaction is complete, same equation here. Now assume the volumes of solution is additive and the water produced in reaction is negligible. So what we know is that limiting reactant, you're gonna start from here, 0.002168 mole of that limiting reactant. It'll complete that one, NO2 minus. Now, so then we are looking for MnO4, right? So the ratio, if you look at here, so 3 NO2, right? 3 NO2 and then 2 MnO4. So you can say times 3 mole of NO2 and then 2 more of MnO4. Okay, so then when you multiply, so then also 1 more of MnO4, right? That one molar mass, then you get molar mass of that. Hold on, when you multiply this one, let's find out mole first then. So then you get that equals, when you multiply 0.001445, okay, mole of MnO4. So that much MnO4 you're gonna use when it's complete. Now, but how many mole of MnO4 you had before? So MnO4 was right here. Okay, that's MnO4 you had before. So 0.002175 minus this one you use, right? 0.01445 more MnO4 you used for the reaction. Then how many more left? then you're gonna get 0.00073 mole of MnO4 minus. That's left, right? Now, so then what is the concentration? Molarity is a mole divided by liter. So that divide by how many liters? So you add up, which is this 1450 and 17. So let's do that. 14. So but that change it to liter. 0.0145 plus 0.01275. So then you will get 0.02725 liter. So you divide that. 0.02725 liter. So when you divide it, 0.0268 molarity of MnO4 minus. Okay, that's how you're gonna get. So what you have to do is here. So using that limiting reactant this mole, and then you find out, there in the equation right here, your molar ratio, 3 mole of this, and then you're gonna use 2 mole of that. So by multiplying this molar ratio, then you can find out this how much mole you used. But remember initially you had this mole, so that was like not limiting reactant, like excessive reactant, right? So that minus the mole you use, then this much more left, MnO4. But they ask you what is the molarity, so divide by liter. So when you add these 2 liter, then you're gonna get 0.02725 liters. So when you divide it, this much molarity. Okay, so we can move on now. Number 3, answer the following questions that apply a reaction of the solution of sulfuric acid H2SO4 and strontium hydroxide. Okay, so that's a SrOH2. SrOH2. So Sr is a 2 plus, OH 1 minus. That's why you need OH2. Okay, write the molecular equation, the complete ionic equation, net ionic equation for this reaction. So okay, let's do that. Then you're gonna add H2SO4, okay, aqueous, plus strontium hydroxide, so SrOH2. Okay, so then you're gonna have, of course, then that's acid and base reaction. You're gonna have a water, so you're gonna have a water H2O. Then you're gonna have the rest of it, which is SrSO4. SO4 is a 2 minus, Sr is a 2 plus, so that's perfectly like this. This is solid because that's a precipitate. Okay, this on liter. Now to balance out the equation here, let's see, you have, so here H2 and H2, so you're gonna need 2. So then 4H, yeah, and then that's it, right? That's the equation you're gonna have. Now, so that's the molecular equation. This is a molecular equation. Now, what about complete ionic equation? So it ionized. So you can say 2H plus, I'm gonna just omit the aqueous state. Okay, now SO4 2 minus, right? You're gonna have only 1, plus this one is also Sr2 plus 2OH minus, right? That becomes precipitate. You always put it like this, not ionized, because it's a solid. And then water is also liter, so 2H2O liter, like that. Okay, so that is a complete ionic equation, and there's no spectator ions. So that means this one is a complete ionic equation and also net ionic equation at the same time. Okay, so both should be same. Now let's move on. Conductivity. Device were placed in a beaker which is initially contained strontium hydroxide in a bullet above the solution. The solution of the sulfuric acid was added. Over time, the two slowly titrated, collected the following data. So if you see that electrolytic data is Y side is a conductivity and this on volume. Okay, so Now, they ask you, first one, why does the initial solution have relatively low conductivity? Okay, why? Why this one is a relatively low conductivity? Because, the thing is, you have this one first, right? So that strontium hydroxide, that one is a weak base, okay? This is a weak base, and then you put that acid, um, slowly you put this acid. So what you can say, why conductivity is very low? Because you can say SrOH 2, right, is only slightly soluble, okay, because because of weak base, okay. Then producing, you can say comma, producing less ions. So you don't have much ions, so that means the conductivity is very low. Now, second one, explain why the conductivity reaches a 0 volt, right? 0 volt and 35. You see that 35, it will reach then 0 here, right? Sulfuric acid has been added. Then why it happened like that? Because that means, this acid-base reaction, so that's the equivalence point is reached. So you can say equivalence point is reached, okay. So it doesn't react any longer. So you have only, right, solid SrSO4 that precipitate, and just water, okay. And there's you can say no free ion, okay. Then they will explain. Now, third one, why does conductivity increase dramatically beyond 35 milliliter of sulfuric acid added? So more sulfuric acid added now, right? So from here, but dramatically it increase. Why is like that? You can say after the equivalence point to reach it, after that there's more you put it the acid. That means you can say excess, right? Excess, much more strong acid. You put it. That means you can say strong electrolyte, right? Strong electrolyte, because it's a very strong acid, right? So then that dissociate into ion, that completely dissociate into ions, okay. That's why it's a dramatically increase that conductivity. All the more ions, then is more conductivity it has. Now C, the last one here. At the end of the addition of 50 milliliter of the sulfuric acid, 100 milliliter of strontium hydroxide, the resulting precipitate was filtered and dried into the drying oven, and yielding a white solid. That means that's the precipitation is a method of 0.619 grams. What was the molarity of initial strontium hydroxide solution? Okay, so you start with that one 0.619 gram of then SrSO4, right? That's solid. So then let's see how many mole of that. So 1 mole of SrSO4 using molarity. Then if you use a periodic table, you're gonna find that 183.684 gram. Okay. Now, so if you just quickly write the equation to find out the molar ratio of reaction side and product side. So let's say SrOH2 plus you put in the that H2SO4, right? That acid and base reaction, right? Sulfuric acid and strontium hydroxide. So then you're gonna get, of course, water and SR. Let's see, that's a 2 plus, and then SO4 is a 2 minus. So you can say just SR SO4. That's a precipitate solid, and then H2O. So now to balance the equation, you see that there's H2. So you're gonna have H2, okay, and SO4 SR. O is a 4. No, O is a 2 here. O is a 2. So you're gonna need 2 H2O, right? And then you have a total 4H. Yeah, it's balanced now. Okay, so then you can say times 1 mole of SrSO4. Okay, now 1 mole of this, 1 mole of that strontium hydroxide. So 1 mole of SrOH2. Okay, then now you multiply, then you're gonna end up with the 0.00337 mole of SrOH2, right? But they ask you what is the molarity, not just mole. So mole divided by liter. So now that divide by what is a liter in the beginning? 100 milliliter of selenium hydroxide. So 100 milliliter is a 0.1 liter. So 0.1 liter, you divide it. Then you're gonna get, you move that decimal to the right. So then 0.0337 molarity of SrOH2 you're gonna have. Okay, so that's how you're gonna do. Okay, that's it for this video.